Hello, am I audible? Okay, so let's begin. Welcome to another problem solving session of the NPTEL course Design of Power Electronic Converters, which is taught by Professor Shabarinath from IT Guwahati. And so this is week 8, which is the last week, and we'll be going over the summary of what was taught in this week and some problems, objective type conceptual problems related to this week's content. So this week was mainly about uh, what actually you will have to choose and decide in the hardware and how to design the PCB and related aspects. So we'll first go over the different sections of the power electronic converters that we have uh, because there will be different portions that you have to focus on individually, and then we'll talk about capacitors, their related, the practical related aspects of the capacitors, how to select them and what are the ratings involved, what are the specifications. Then there was uh, a lot of focus on PCB designing and some focus on the different grounds and references that are encountered in an actual converter. So let's start with the sections of power converters. So as you can see, I've listed the main sections that were mentioned in the course. So I've separated the power electronics and the gate driver sections. In the course, the gate drivers was mentioned inside the power electronics. Then we'll have the controller, we'll have some sensing circuits, we'll have some interfacing circuits, we'll have power supplies. So this will be basically the low voltage power supplies that will be given to the gate driver, the controller, the sensing circuits. And there are cooling uh, aspects, that is the heat sinks, the fans, it may be thermal, liquid cooling or other aspects. And there is also finally the enclosure. And so this depends on what kind of product it is. So if it is like a standalone product, like a charger or an inverter, then you will have an enclosure, which is the converter will be placed inside this enclosure. Or if you have a converter that is part of a bigger system, like inside a vehicle, you can have a converter, especially an electric vehicle. So there, the enclosure may not be required because the whole engine or the whole powertrain is enclosed in something else, like the engine has its own covering. So enclosure depends on the application. So I thought instead of going over again the content that was covered in the course, I will actually choose a different converter. So this is uh, a boost sorry, this is a three-phase motor drive by Wolfspeed, and the part number of this whole converter is shown here. So if you search for this, you will find the reference design by Wolfspeed online. So they have provided the schematic, they have provided how they like the PCB layouts, the design of the PCB, even the bill of materials. So they have provided all these things, and it is available for free online. Then you can basically see it's a reference design. You can use it to check your design. Oh, somebody is saying I'm not audible. Can everybody hear me?
Audible, bro.
Okay, so I think it may be something on their end. So you check your connection or your volume. So this is I was talking about this converter. It's a three-phase motor drive by Wolfspeed, and we'll see all these different sections for this converter. So if you uh, search for this converter, you will find they have given the circuit diagram. So it is three-phase AC is the input, and then it will drive a three-phase motor. And in between, first of all, we have EMI filter and some protection circuits. Then we have a three-phase rectifier, so uncontrolled rectifier. So we will get a DC voltage here, and this DC voltage will be usually a fixed value, because if the AC side is fixed, like 415 volt AC, then this will get a fixed voltage. Uh, it will not be regulated. So if the AC has any fluctuations, this will also have those fluctuations. And then we have a two-level voltage source inverter made of using MOSFETs, and this we can drive using our controller, our gate drive, and then we can get the required voltage and frequency at the output. So this portion that is shown in black is the power electronic part. And then all the portions in blue are the other portions. So it has some sensors like current sensors, voltage sensors, DC bus voltage measurement. It has an encoder for speed measurement. Then there's a controller. There will be gate drive signals. So those are separate sections. The power electronic portion would be the inverter portion, the rectifier portion, even the EMI filter. So this will be the power electronics portion. And so if he's so this converter, particular converter, may not have any snubbers, but if it had, those snubbers would also be included in the power electronic portion. And then we will have the gate driver. So you may include it in the power electronic or you may put it separately. So because we have here 6 control switches, so we will have 6 gate drivers. And as you can see in this inverter, we have 3 low side gate drivers and 3 high side gate drivers. And we have seen in previous sections that high side gate drivers, the source of the MOSFET is not at a fixed voltage. The voltage keeps on varying. And that is why we need some isolated power supply to drive that gate driver. So in this converter, what they have done is, so they have 6 gate driver ICs. So that is that cannot be. So you have to require 6 gate driver ICs. But for the power supply, for the low side gate drivers, they have a single power supply, because as you can see, the 3 low side gate devices MOSFETs, the source are connected to the same point. So they have one isolated voltage, isolated DC-DC converter, which provides the input is 12 volt and the output is plus 15 minus 3 volts. So one of these they have used, and this provides the voltage supply to all the 3 gate drivers of the low side switches. So this is one low side gate driver, so it has the supply and it has the gate driver IC. The other two will only have the gate driver IC. They will not have a separate supply because this same voltage is used for those two as well. But for the high side gate drivers, since for the 3 high side gate drivers, the 3 sources of these MOSFETs, they are at different potentials. So that is why they have 3 separate DC-DC, isolated DC-DC supplies for the 3 high side gate drivers. So this is how they have done. So you can see in this way they have reduced, instead of using 6 isolated DC-DC converters, they've only used 4. So they have saved up on the space and the costs as well. So this was the gate driver section. Next, we have the controller. So the controller in general, it can be a digital controller, an analog controller. The analog controller is usually made of some op-amp circuits where you want to achieve a particular transfer function for your controller. So you can use some op-amps to produce the PI circuit or some other transfer function, or there are separate controller ICs that can be used to, they will provide particular transfer function inside. So you just have to put that IC in your circuit and give the necessary connections, and it will give you the controlling action. The other option which is used here is a digital controller. So here they have used this digital controller by Texas Instruments, and it is connected on the main power board, and then all the whatever is sensed from the converter goes into the ADCs of this digital controller, and then it provides the PWM outputs, which then go to the gate drivers and then drive the switches. So this controller is another section, and it usually will have its separate related circuits in the schematic. Then we have some sensing circuits. So in this case, we have voltage sensing, we have the DC voltage sensing. We also have option to sense the phase output voltages. Then we have current sensing using shunt resistors. This one also has an encoder for speed sensing. The circuit I have not shown here, but if you search for the reference design, you will find also they have a speed sensing encoder. Uh, these 6 MOSFETs are actually in one module, and that module also has a thermistor for temperature sensing. So all of these aspects are sensed and they are given to the microcontroller. So the sensing can be done in various ways. So the voltage sensing is done using a resistor divider. So we have very high resistance here, and then one of the resistances we have taken an output, and then this goes to an isolated uh, or basically an isolated amplifier. So this provides isolation. So the input ground is not the same as the output ground. It provides isolation, and then this isolated one output goes to the microcontroller or the DSP. And similarly, the current sensor also, we have a very small resistance, a high precision small resistance. Small resistance because the current that will go through, if the resistance is large, then it will create a lot of losses. So the resistance is very small, and the resistance is very precisely, the resistance is made very precisely so that we get a voltage that is proportional to the current. And by measuring that voltage, we can get the current that is flowing. And then again, after that uh, resistor, we have this circuit. It will have some RC uh, filtering, and then we have another isolator. So this will basically isolate the input side and output side. So if there is any uh, fault or condition on the controller side, that is not propagated to uh, the power side. So any fault or any high current that occurs in the power side, that should not propagate or damage your controller. And also it provides some more noise immunity. So so these are not necessary. You can have non-isolated sensing as well. So isolated sensing provides better noise immunity, and as I mentioned, in case of uh, some faults or uh, overcurrent and over voltage, this isolation actually helps. So sensing circuits also form another aspect of your power converters. Then we have interfacing circuits. So what this means is your controller and your power converter, so they may have different requirements, different voltage ratings and different current ratings. So that is why we sometimes require some additional circuitry to transform uh, these voltages and currents into different values. So for example, this circuit is shown here for voltage conditioning. So it is basically a voltage sensing circuit. The voltage that is sensed is actually the output of the inverter with respect to the motor ground. So this voltage will be positive as well as negative. And this voltage is sensed and then it goes to the microcontroller. But the microcontroller has a requirement that it will only allow, or it can only sense voltages between 0 to 3 volts. So first of all, we have to scale the voltage out, the sensed voltage. So the sensing voltage, if it is between 12 plus minus 1200 volt, we have to scale it down. And also we have to give an offset. So that the voltage does not go to negative. We can only have positive voltages between 0 to 3 at the output. So what is done, it is given an offset of 1.65 volt, so that when there is 0 volts that is being sensed, we will get 1.65 volt at the output. And then when a positive voltage is being sensed, the output will give uh, more than 1.65 volts. And for negative voltages that are being sensed, the output will give less than 1.65 volts. So in this way, this kind of a op-amp circuitry, it is used to interface between the sensed output and the microcontroller input, or the ADC that goes to the microcontroller. And similarly, we can have other interfacing circuits as well, like we can have buffers so that the microcontroller is not loaded. Microcontroller does not draw or sink very high current. So we have other buffer ICs that can do this job. In general, we will have the kind of an interfacing circuit between different sections of the power converters that we have. So next, we can also have, so all these circuits that we talked about, that is the gate drive circuit, the sensing circuit, or the interfacing circuit, they all require some power supplies. For example, if we see the gate driver, so it has this Morata DC-DC converter. It has plus 12 volt supply. The gate driver IC has plus 5 volt supply. Similarly, the sensing circuits, they have plus 5 volt on one side and plus 3.3 volt on another side. The interfacing circuit also has plus 3.3 volt. We also require this 1.65 volts. So all these voltages are required for the operation of these circuits. So this can be done, either we can have a separate voltage that can come from the outside. So we can have, let's say, 12 volts that comes from the outside, and then we can have uh, some other linear regulators that will provide us these 5 volts, 3.3 volts. In this case, what they have done is they take the full input voltage or the DC voltage. So the DC bus, they take this voltage and it goes to this IC, which is actually a flyback uh, converter, or it is a flyback controller. The circuitry of the flyback is has to be connected externally, and then this flyback converter, it will produce 12 volts isolated from the DC bus. And then using these 12 volts, we can have separate ICs, separate regulators to produce the 5 volt, the 3.3 volts. So this kind of a power supply, this is called an auxiliary power supply. It can also be present inside the converter. And lastly, the cooling and enclosure. So it depends on what kind of cooling we have. So here they have a heatsink and attached fans. In this particular case, they don't have an enclosure because it's just a reference design. They are not. It is not intended as a product. But if you have a product, you will also have an enclosure usually, so that all these things are not exposed. So when the user, they have to handle the converter, uh, they can handle it easily, and also it will provide immunity for EMI, as we have seen previously. So these are the different sections of power converters that we will have, and you have to pay attention. At least you have to know something about all of these sections in order to make a working converter. So next we can talk about the different types of capacitors. So we have seen different capacitors that are used inside the converter. We have, in DC-DC converters, we have capacitors at the output of the converter. We can also have capacitors at the input of the converter, and these usually have DC voltages. But in other converters and in other aspects like the EMI filters or other filters in AC converters, we can also have capacitors which will have AC voltages across them. And we can also have small capacitors like the snubber capacitors. They will have varying voltages. So the voltage will vary between 0 and the DC bus voltage, and they will change very fast, those voltages, but the capacitor value is small. So all these aspects, you have to choose different types of capacitors that are available, and you have to choose from them based on your requirement. So the three main type of capacitors that are available are the electrolytic capacitors, secondly the film capacitors, and lastly we have ceramic capacitors. And in order to choose between them, the first thing that you have to consider are the the capacitor value that you require, and the voltage rating of the capacitor. So that is the maximum voltage that will be imposed upon that capacitor. So as you can see in this graph, uh, these three different types of capacitors, they will have different applications. So first of all, the electrolytic capacitors, we can have aluminum based electrolytic capacitors or tantalum based electrolytic capacitors. So these capacitors are usually available in very high capacitances. So as you can see, the x-axis is capacitance axis in the logarithmic scale. So the aluminum capacitors are actually available in relatively high capacitance values, but the voltage rating is limited. So if you want very high capacitance, then uh, aluminum electrolytic capacitors are a good option. However, they have some limitations. So first of all, these are uh, polar capacitors. So the positive one has to be connected to a particular portion, the negative one has to be connected to a particular portion, and usually uh, they cannot be used for AC, but there are special capacitors for AC, and also they actually have relatively low lifetime, or they have a very higher failure rate compared to the other capacitors, and they also have higher parasitic inductances usually. And then the next capacitors that we have are the film capacitors. So they are available in lesser capacitance values, but the voltage rating can go much higher. So the plastic film capacitors and power capacitors that are shown here, they also come in the film capacitor aspect. So these are present available in lower capacitance values but higher voltages. And lastly, we have ceramic capacitors, and these have again very high, they can have very high voltage ratings, but the capacitance values are limited. And usually these ceramic capacitors, they have very low parasitic inductances, and as well as they have a very small form factor, but again they are not available in very high capacitance values. So these are some of the images that we'll have. So on the top we have electrolytic capacitors, and as I mentioned, these are polar capacitors, so or polarized capacitors. So one of them has to be connected to the positive, the other has to be connected to the negative. You cannot interchange the terminals, and usually the one of the terminals is marked so you can see. So they are available in through hole arrangement. So through hole means they will go through the PCB on one side and they will come out the other side. So all these which have these leads, these are through hole components. And then we also have SMD, which is surface mount devices. That means they only attach to one side of the PCB. They do not go through the other side. But SMDs are usually smaller. Similarly, we can have the same thing for film capacitors as well, but these are not polarized. We can then interchange these connections. And on the bottom right, or in this middle, we have the ceramic capacitors. Again, through hole as well as SMD are available, and these are usually much smaller than the film and the electrolytic capacitors that are shown here. So now, ideally, the capacitors should only have capacitance uh, inside it, but practically you will have some parasitic inductance and as well as parasitic resistance. Uh, that will be because of the dielectric and because of the leads that will come out. So all these things will be present. And then you can see, based if we ignore the resistance, we can actually see the impedance of uh, this whole arrangement, and we will have a resonant frequency, and at this resonant frequency basically the inductive reactance will be equal to the capacitive reactance, and before this resonant frequency the capacitive nature of the capacitor will be dominant, and after the resonant frequency, if we go beyond this frequency, the inductive nature will be dominant. So this uh, effectively the capacitor will behave like an inductor beyond the resonant frequency. So that is why you have to take care of the working frequency that you will have, whether it is 100 kilohertz or more than that. You have to make sure that it is less than the resonant frequency of the capacitor. So these kinds of graphs, they may be provided by the manufacturer. So you have to see that your working frequency, it is before the resonant frequency range. And you can see for different types of capacitors, these frequency, the impedance graphs are different. For example, the MLCC, which is shown, which means multi-layer ceramic capacitors. So these are ceramic capacitors. They have a very sharp uh, impedance graph compared to this aluminum electrolytic capacitors. They have a relatively gradual slope of this impedance graph. But in any case, you want to operate your converter before this resonant frequency point. Also, because of this ESR, there will be some losses inside the capacitor. So whenever we have a capacitor that is attached, it will carry some current. And even though uh, on an average, the current will have zero average, but it will have some RMS value, and that RMS value, because of this ESR, the equivalent series resistance, it will create some losses and it will create some heating. So usually this ESR is given in the data sheet as dissipation factor. So if we find the vector uh, diagram of this capacitor, we'll have a capacitive uh, phasor, and we'll also have the phasor related to the ESR. And if we ignore the ESL, the impedance will make an angle delta with the capacitive portion, and then the tangent of this delta angle will be given by this expression that is shown. So if this tan dissipation factor tan delta is given in the data sheet, then and you know the capacitance value, then you can find the resistance at different frequencies. So this is usually or sometimes given in the data sheets of the capacitor, or sometimes they actually give the ESR directly. And they can also give the ESL, the nominal ESL of different capacitors. And then we have some other capacitor ratings. We can have the current ripple, or it is basically how much RMS current the capacitor can handle before it heats up too much and it can no longer operate normally. So because of the RMS current, the capacitor will heat up because there will be some losses in the ESR. So that is why, to limit the heat to a particular value, to limit the temperature to a particular value, there will be a particular maximum RMS current rating. Similarly, there will be a DVDT rating. This is important for snubber capacitors where we have high DVDTs, and the failure rate will also be given in the capacitor. And so this you may see if you want to design your converters for long duration, or if you want to converter to have a long life, then the failure rate you can consider. And in general, the electrolytic capacitors, they have a very or relatively higher failure rate compared to the film and ceramic capacitors. So next we can also see some other components related to the power converters. First of all, so as I mentioned, the components can be of two types. We can have through-hole components. We can also have surface mount or SMD, surface mount devices. And through-hole, as it's shown here, they actually go through the through the PCB. So they go through one side and they come out the other side, and then they are soldered. The surface mount devices, they actually are placed only on one side, so whether on the top or the bottom, and then they are soldered. So they take up less space, and they on the other side we can have different components, but usually they have smaller ratings because of their smaller size. The ratings are also smaller, so the resistance For example, here resistance is shown. The resistance power rating will be smaller for SMD devices compared to the through-hole devices. So so as you can see here, for resistors, if you want to uh, use a resistor in your circuit, the resistor will have three ratings that are important. One is the value of the resistance that you want. Another is the tolerance. So that means because of the manufacturing inconsistencies, your resistor may not have exactly the value that it is written uh, on the data sheet, but it will have some tolerance. So it may be, for example, here it is written 5%. So that means the resistance value may be plus or minus 5%. So if it had to be 15 ohm, it can be 15 plus 5% or 15 minus 5%. So that is the tolerance. And next we have the power rating. So because resistances, whatever current they carry, they will lead to losses, I square R losses, and that loss will be generated as heat. So that is why your resistor will have a power rating of how much heat it can handle. And as the power rating increases, the size of the resistance will also increase. So, so in general, if you have a resistor on the power side, that is the power electronic component section, for example, you have a resistance like in your snubber section, or if you have resistance in the for voltage sensing, then you have to consider how much losses it has to dissipate, and then you have to choose your resistance power rating based on the losses that you are expecting. Next, we will also have the connectors that we'll use to supply the voltages and take the outputs out, or connect the inductors, transformers. So you have to consider the voltage and current ratings of those connectors as well. And the equipment that is used, the main equipment that we have to use when you test your converters are the oscilloscopes and isolated probes. So oscilloscopes are very important for testing your components to your converters. So you have to get familiar with oscilloscopes, and this is this can be mainly done by actually uh, handling the oscilloscope and doing the measurements. It is I mean, it is very difficult to explain it in an online session. You have to actually do it hands-on, and then you will understand how to use the oscilloscopes. But you can read the data sheets and the manuals to see how they work. And an important uh, aspect in power converters is that when we are measuring different voltages, usually these oscilloscopes, they have different channels to measure different voltages simultaneously. But usually these multiple channels, they have the same ground. So internally, the ground of each of these three channels, they are connected to the same point. So that is usually the case. But if you, in power converters, when you want to measure different multiple voltages, these voltages may not necessarily have the same ground. So for example, if we have a half bridge and we want to measure the voltage across both of the switches, the drain to source voltage of both the switches, then the ground of both of these two measurements is not the same. And if we connect using a normal probe directly to the oscilloscope, because the grounds are internally shorted or they are connected together, so this will short the two switches that we have. So that is why we have to use what is called an isolated probe. So this basically isolates the measurement points and the point that goes to the oscilloscope, so that then you can measure multiple voltages with different grounds without having to worry about uh, shorting these different voltages. So this is some of the basic equipments that we use to test our converters. The rest of the components are covered in the course. I cannot go into detail because of the time limitation. So, so I'll just talk about some PCB designing basic steps. So the PCB designing, it basically starts from your circuit diagram. And usually it is not very simple circuit diagram. It is not just the converter as we saw it. We have other sections as well, and they all of these have to be placed on a single PCB board, or they have to be connected multiple PCBs, and then they have to be connected together. So this schematic is actually very complicated in general. So this is the schematic, the power side schematic of the converter that I talked about previously, the three-phase motor drive. So as I mentioned, we start from the three-phase AC, then we have a rectifier module, and then we get a DC bus. We have some capacitors, DC link capacitors that are connected, and then we have the inverter, three-phase inverter, and then it is connected to the current measurements, and which goes to the output. So this is the power side schematic, and then we also saw the other schematics of the gate drivers, the sensing circuits. So all of these are actually made in your PCB designing software. And then the second step is that the different components that you have, they have to be assigned what is called a footprint. So each component has to be assigned a footprint. Footprint is basically the dimensions and the pins uh, that will be occurring in the actual component. So if we have a MOSFET, for example, it will have the three legs or more than three. It can also have four legs, but let's stick to three legs. It can have the drain, gate, and source. And what is the uh, spacing between these three legs? What is the size of the hole that has to be done in the PCB for these three legs? So all of these is determined by the component footprint. So similarly, we can have footprints for the capacitors, for different ICs, uh, for resistors, for inductors, transformers. So all of these you have to assign to each component its own footprint. And this is essential because if you mismatch the footprint, then when you actually get your IC or your device, it may not fit inside your uh, the PCB. So you have to make sure the the device or the IC, it has you have to make sure that you are choosing your particular footprint properly. And usually at the end of each data sheet, for example, if you have a switch or an IC, at the end of the data sheet, they will be giving the different dimensions of that IC. For example, they will give what is the length and width of the IC, what is the size of the pins of the IC, what is uh, the length between two pins. So all of these measurements, they are used to make the footprint of the component. And then finally, once you have the footprint, you have to place the components on the PCB, and then you have to route. So routing means connecting between different components using PCB traces. For example, this is the converter that we have been talking about, uh, the PCB of that converter, and they have shown the different components and where they are placed. So this A point is the input AC terminal, and the B portion, this whole B portion is actually the EMI filtering. So this can be the common mode choke. Uh, there can be different capacitors here. The C portion, this small C portion, is actually the three-phase diode rectifier. So it comes in one single package. So they're not six separate diodes. They are actually, I mean, they come in one package. They are six diodes, but they come in one package. You will have the two DC bus terminals, and you will have the three midpoint terminals of the rectifier. Then we have some protective circuits. This E portion is the gate drive portion, and as I mentioned, they have four isolated DC-DC converters, and they will have six uh, driver ICs, as you can see here, and then these are connected to the MOSFET. The MOSFET is actually this one single module with six MOSFETs, and then on top of this MOSFET module is actually your gate driver. They have a separate, sorry, your controller, and we saw the controller card that they have. It is connected vertically in this case, and then they have different measurement sections as well. On the bottom they have the heat sink and the fans they will also have, and the bottom they also have the DC link capacitors, the aluminum electrolytic DC link capacitors. So this is how you place the components. So there are some rules on what is the optimum placing, or uh, what is bad placing and what is good placement, and then you route the different components. I cannot go into the details, but we can have some basic principles. So when you route, you have to understand that the PCB traces, which is basically the copper lines where the current will flow, they will have its own parasitics. It will have some resistance, because just any component, any conductor will have resistance, and it will also have parasitic inductance. It will produce a magnetic field if the current is varying, and that will lead to inductance. If there are multiple traces, and there will be trace and the ground, it will have capacitance related to it. And so all of these things will add to parasitic, and they may lead to noise, they may lead to over voltages, they may lead to voltage spikes. Uh, so all of these things you have to consider when you design your converter. Next, you also have to consider the copper thickness and trace width. So this is your trace. It has a thickness T and it has a width W. And you can understand, if I increase the thickness or the width, then the resistance of this trace will reduce. And if the resistance reduces, then whatever the current is carried, the loss, that is the I square R loss, also reduces. So that is why if you want to decide on the copper thickness and trace width, this is usually determined by the current capacity. So how much current you want to flow, it will have a related loss and related temperature rise. And so you will have a specification on how much temperature rise you can manage. And depending on that temperature rise, you will have to choose your copper thickness and your trace width. And the copper thickness will have some defined values that the PCB manufacturer will allow. So like 35 micro or 60 micrometer. So these are uh, the standard thicknesses that are used, and the trace width you can vary in any value that you want. And based on that, you have to decide what will be the trace width, the thickness, based on the current capacity. Next, when we have multiple traces or multiple the pads or multiple copper portions, you have to keep some distance between these two pads uh, or traces. And this distance is usually determined by the voltage difference that occurs between these two traces. So based on what is the voltage potential difference between them, a certain minimum spacing is required. So as you increase the voltage potential difference between these two traces, then the spacing also increases. So these distances are given in different calculators and different graphs or tables, and you have to consult those tables to find out what is the voltage clearance that you have to provide between multiple traces. And lastly, ground planes are usually used. So whenever there is a trace, it will carry a current. To complete the circuit, you also require a return path. And that return path goes through the ground. line, and that is why usually we have a ground plane. A full plane of a PCB layer is dedicated to the ground so that the current itself will follow the path of minimum resistance, and it will reduce the resistance and the inductance, parasitic inductances. And in general, the ground plane will also provide some noise immunity, and there are some other rules as well related to the ground plane. But in general, one plane is reserved for ground as to minimize these parasitic uh, resistances and inductances. So last thing I will talk about in this aspect is uh, for the power side of the converter, uh, uh, you have to consider the loops which will have high DIGT and the nodes which will have high DVDT. So for example, we have here a boost converter circuit, and the green loop that is shown here, the current through this green loop is shown here. It is an inductor current, and the DIDT of this inductor current is actually relatively low. But the current that flows through the MOSFET and through the diode, it is actually a pulsed current. So sometimes it is zero and then it goes to a very high value and then again goes to zero. So that is why these currents will have very high DIDT. So if the loop area of this high DIDT current is large, then you have a larger inductance. And because the DIDT is high, and if the inductance is also high, or the parasitic inductance in this loop, then it will lead to LDIDT voltages. So it will lead to voltage spikes. So that is why you want to minimize uh, this high DIDT loop. Similarly, you will also have some nodes in your converter with high DVDT. So the switching nodes, for example, in this boost converter, this blue portion, it has the voltage switches between 0 and the output voltage. So that is why it has very high DVDT. And this high DVDT will create capacitive currents, and that can cause problems as well, some noise issues. So that is why you want to minimize the area of this high DVDT. So, so whenever you are designing, you have to follow these steps and you have to take all these aspects into consideration. And so these things usually come with experience. So you start with the reference design, you see how previously people have made their converters, and you take inspiration from them and you start your converter, and then you make one prototype and you test it, you see how it is working, and then step by step in the next iteration you may improve on some aspects. And so this is how the converter design and manufacturer is done. So lastly, we will talk about the grounds or different references that are present in the converters. So there will be different power grounds in a converter. So in the power electronic portion, so for example, if we have this inverter portion, we have a DC plus and a DC minus. This DC minus is what I'm calling a power ground. And also when it actually goes to the motor will also have another ground. So these are the different power grounds that will be there in your converter. So they may not necessarily be connected together. So for example, here the DC minus, we will not connect it to the neutral of the motor. So these are not connected, but the some other grounds that are present in your converter like analog ground, digital ground, these may be connected together. So for example, the analog ground is shown here. So analog, because the first ground that we talk about, these are related to your power voltage and current ratings. So these have high voltage and current ratings. This is the ground related to uh, high power components. Then in your converter, we saw, we also have low power components like your sensing circuits, your conditioning or interfacing circuits, and your microcontroller or your analog or digital controller, they are low power components, and that is why they have a separate ground. So the analog components will have an analog ground. So by analog components, we mean that the voltages, they can vary between 0 to, let's say, 3 or 5 volt. Anywhere in between, these voltages can vary. So these are analog voltages. By digital ground, we mean related to the digital controller, and there we can have voltages that are either on or off. So it will be 0 or 3.3, like in case of your PWM voltages. And in some other cases also we have these kind of digital voltages, and those aspects will have a separate ground. And lastly, we will have a ground which is called the chassis ground. So the converter enclosure will be connected to, it may be earthed or it may not be earthed, but it is also connected to either the EMI filter ground or the one of the power grounds as well. It may be connected. So that is called the chassis ground. And then all of these grounds may be connected together or they may not be. They may be isolated from one another. So for example, in this converter that is shown, the power ground is actually isolated from the analog or digital ground, but the analog and digital ground, these two grounds are actually connected together in this converter. And this converter does not have a chassis, so it will not have a chassis ground, but in general you may have a chassis ground as well. And so these grounds, when you are connecting these grounds or routing these grounds in your PCB, you have to make sure, you have to follow some rules. You have to make sure that ground loops are not formed. These ground loops will create interference from one circuit to another, and they may also pick up some noise, and they may also provide paths for undesirable currents. So for example, if there is an appliance, it has some current that is going to the ground, but a ground loop is present, so it will provide a path for this current, and it may go to undesirable paths. So when you are designing your converter, you have to uh, keep into account your ground loops, and you have to design them carefully as well. So this was basically the summary of the content that was taught in the week. So I cannot obviously go into the PCB design tutorial because we don't have enough time. I will just go into the problems, uh, some objective type problems related to these topics that was covered. So we can now have a short break before we go into these topics. So we'll continue at 4:05 p.m. Okay, so during that time we can have a short break. Okay, so let's continue. So the first problem is planes or polygons of different types of ground should be connected in which node. So plane basically means in a PCB, so like I mentioned, usually the ground, you will have a plane dedicated to the ground, because in a multi-layer PCB, on one layer of the PCB you may have connections between different points. On a different layer you may have a plane, a full uh, copper portion that is dedicated for a ground, or it may be like is shown here. On the same layer, one portion is for the connections between the different traces, and then another portion is for the ground. So that can also be done. And then you can have multiple sections, like we saw. We can have a ground uh, for the power related aspects. We can also have ground for the analog, the digital, the chassis. But the chassis will not be in the PCB, but the first three will be in the PCB. So in the PCB, the planes of different types of ground should be connected in which type of a node. So basically, so C and D are not exactly uh, sensible options. Uh, so the question is between delta connection or a star connection. So for example, if we have these three planes which are shown in this light blue, light green, and yellow. So one option is we can connect them in delta like this. And another option is we can connect them together in a star type of a connection that is shown on the right. So the problem with the left side connection is that these three connections, they may have different impedances. So which will lead to different impedances in these three different ground. That the potential in the three grounds may be different. It may also lead to ground loops that we saw. For example, if we see from the blue to the yellow, one connection is directly and another connection is through the green plane. So that leads to a ground plane, a ground loop, and that may lead to some other interference. So in general, this kind of a connection is not preferred. What will be preferred is what is shown on the right, so that we connect them together. So even though this portion will have some impedance as well, but it is minimized, or we try to equalize between the three grounds. So in general, we will prefer a star type of a connection compared to a delta type of a connection. The second question is, which of these introduces noise from one circuit to another? Whether it's a star node, low power level, ground loop, or film capacitor. So can any of you guys guess the answer? Yes, so this we discussed previously, the ground loops that we talked about, they may introduce noise, and uh, in the course it was analytically shown how because of the presence of uh, this ground loop, there will be some uh, current that comes from the digital ground circuit to the analog circuit. So that leads to that creates interference and noise. And similarly, on the bottom side, uh, if we have an appliance and that has some leakage current or some common mode current that goes from through the ground, once we have this ground loop, so we have another path. So that path will create noise in these component 1 and component 2. So the answer is the ground loop will introduce noise from one circuit to another. Third question is that which of these introduces a high impedance between the sensor and the controller? So whether it is the analog sensor, whether it is a gate driver or a Sallen key filter or a buffer. So So we talked about this very uh, briefly, but buffer can be used between two components as part of the interfacing circuits. So it can have multiple uh, benefits or multiple uses. One use is, as is shown here, it provides a high impedance between two circuits. So the what is usually the case is the controller, it cannot provide high currents or it cannot sink high currents. So that is why you want that whatever is connected to the controller, it should have high impedance so that it will not draw any current, as well as the it should not also give a lot of current to the controller. So that is why we can use a buffer for this. And we can also use a buffer. So for example, here a buffer is used to basically uh, increase the voltage level. So the controller provides a voltage output for the PWM for the gate driver, which is 0 to 3.3 volts. So to increase that voltage level to 5 volts, we have a buffer IC, and it will also provide the impedance aspect, but it will also provide some level shifting as well. And then it will go to the gate driver. So the buffer is used in the interfacing circuit for multiple purposes, and one of the purposes is high impedance between the controller and the other aspects. So the next question is about different types of capacitors. And so the three types of capacitors that we saw, they can also have some subtypes as well. So this was actually mentioned in the course. Uh, which of these are film capacitors? So someone is actually saying C, which is not correct in this case. So actually, what was mentioned in the course was that the electrolytic capacitors can be of two types, aluminum or tantalum. Film capacitors can have these three types. They actually can have more, but these three were mentioned in the course. So polyester, polypropylene, or polystyrene. And ceramic capacitors can have single layer or multi-layer. So these are the different types of capacitors. For film capacitors, out of these four, B and C are the film capacitors. The A and C are electrolytic capacitors. So the answer to this one is B and C. So next question is, which type of capacitor from below can be manufactured with the highest capacitance? So this we saw in when we introduced the capacitors. So yes, the answer is so out of these four, if we talk about the highest one, then that will be the aluminum electrolytic capacitors or the electrolytic capacitors in general. So they can have the highest capacitance out of these four. So for this one, it is so ultra high voltage ceramic. So as I mentioned, as we go in high voltage for the ceramic capacitors, the capacitance value actually reduces. So that is why the fourth one is not the answer to this one. So in general, it is true that for all of the different types of capacitors that we saw, as we increase the voltage rating, the capacitor value reduces. The capacitance value reduces. So, but ceramic in general, they do not have very high values. And as we go for high voltage, the values will reduce further. So the answer to this one is only the electrolytic one. So next we have a question about the ESR of the capacitor, and it varies with which of these values or which of these aspects: the temperature, the frequency, the dVdt rating, or the ripple current. So this question is basically talking about once we have a capacitor, it will have a particular ESR, but this ESR will not be constant. It will actually show variation with respect to one or more of these uh, aspects. So this was covered in the course, main course, and Basically, as the temperature changes, the ESR will also change. And this also depends on which type of capacitor it is. So for example, here there are shown two electrolytic capacitors. One is wet aluminum electrolytic capacitors, another is solid. And as you can see, for the wet case, the variation is a lot more than the solid case. And similarly, it will be the case with film and ceramic. They will have different variations, but in general, the ESR will vary with temperature and it will also vary with the frequency. So the ESR itself will vary with the frequency, and then the impedance, of course, will vary with the frequency as well. But the DVDT rating and ripple current is not necessarily, it will not be provide any variation in the ESR. So the next question is the ground which is connected to the enclosure of a power electronic converter is known as which of these four grounds? So this we talked about. So which of these do you think? Yes, so it is called the chassis ground. The analog ground is, so the first two grounds are for, and so realize these are just names. You need not name the ground particular value, but you have to understand that a particular ground has some different features. So the power ground will have very high voltages and currents. I mean, it will not have high voltage, but it will have high currents through it. It may also have high voltage as well. So if you have multiple converters, for example, if you have a what is called a CHB converter, which has cascaded H bridges, and so each H bridge will have a ground, and that ground will can have a different potential. It may not necessarily be at zero potential. So, but in general, power grounds will have high voltages and currents, and so that separates it from the other grounds like the analog and digital ground. These are usually at low power and low voltage currents, and in between them, the analog and digital ground, the analog portion of the circuit, in this, it will have usually uh, uh, what is called multiple, it can have different values between 0 and some 5 volts or 12 volts or 3 volts, whatever the case. It can have any voltage between them, while the digital circuits, they will usually have some fixed voltages between 0 and some 3.3, or so they will only change in these blocks. They will not change. You will not have a voltage level, constant level between them. So that is what separates digital ground and analog ground. And then the chassis ground is actually what is connected to the enclosure. So this is the seventh question, and the last question that we have for today is the clearance between two nearby traces is decided by which of these conditions? Whether it is decided by the currents that are carried by them, the voltage difference between them, the temperature difference between them, or the impedance between them. Yes, so this we briefly mentioned. Uh, so there are two aspects when you are deciding your the trace, what kind of a trace you will draw on your PCB. So one is the width of the trace, the thickness of the trace. Those things are determined by the currents that are carried by the trace. And then between multiple traces or pads, between different pads as well, you will have to put some distance between them, and that distance is decided by the voltage difference. If it's a higher voltage difference, then you may require a larger distance between these two traces. And similarly, for if the distance is less, then the uh, voltage difference that they can survive is will also be less. So the clearance is decided by the voltage difference. So I hope that was understood. And so these were all the problems that we had for this topic. And so this was the last session. So if you have any questions related to this topic or any of the previous topics, you can ask in the chat or in on the microphone by unmuting yourself. So if you have any questions, you can ask now. So if there are no questions, then so those who want to leave, they can leave. Building your own PCB. So it was actually shown in the last lecture of the actual course. So if you see that they had a PCB tutorial where you have to follow all these steps that we mentioned. You have to first design your circuit schematic, then you have to assign footprint of each of the components, and then you have to place the components on your PCB and then uh, connect the different components as in the circuit. So but that is a very involved process and I cannot summarize it right now, but I will refer you to in the course. It is basically the very last lecture, that is basically a PCB design tutorial. So once you have made that PCB, you can actually get it printed from services, different manufacturers like PCB Power. So the etching part is actually uh, you cannot do it by yourself. So in the modern PCBs that we have different manufacturers for these PCBs. So you only have to make the design files. So at the end, you will make some design files in particular format, and then you will give it to a PCB manufacturer. And you will have to mention what is the size of your PCB, how many layers do you want, what will be the thickness of the copper, and uh, and even things like color of the PCB and all these things you can decide. And then they will uh, tell you how much how much it will cost and how much time it will take. And then if you agree to those things, and then you can make the payment, and you will get the PCB. They will make you the PCB. So the etching is not it is not done by hand or anything. It is actually done by different machines that they have, the PCB manufacturers they have. So one manufacturer that we use is called PCB Power. Yes, so PCB Power is something that we use in our lab. There may be others that I'm not familiar with, but PCB Power, if you search online, you will find. And then they have the PCB manufacturer process, and then you can choose the dimensions and the number of layers that we have. This will basically determine the cost of the PCB. So you have to provide the design files. And then those design files you can see in the course, the last lecture, how to make those design files. So I hope that is clear. Thank you all as well for joining. So if you have any more questions, I'll be here for some time. You can ask. Uh, or as well, I have given my email multiple times, so I can give it again this last time. So if you want to uh, have any more doubts or if you want to ask or clarify something, you can email me as well.